After understanding the process of determining the derivative of a given function, in this case complex function, using a definition, let's look forward into the proper rules of differentiation. For these rules, we'll no longer use the idea of the definition, but basically, these rules are just derived from the definition of the derivative itself. We're going to list here some of those rules as part of a review, at the same time the integration for complex function or complex numbers, before we will have some examples later on. Of course, we have a lot of them. You can also name them as their specific names for the rules, but allow me to write them here step by step, or one by one rather. Let's start with the first rule. This is the rule for the sum of functions. Let's say we have here f of z plus g of z. Okay, so we have the sum of two functions. The derivative, of this sum with respect to z is equivalent to the derivative of the first function f of z with respect to z plus the derivative of your second function g of z with respect to z. This would mean that, of course, just like in our real numbers, the derivative of a polynomial function is equivalent to the sum or the combination, depending this is sum, right? Addition of the derivative of the individual terms or functions. Of course, this is equivalent to the derivative of your first plus the derivative of your second function. These two are just the same. They just have different notations, but basically, the notation for this stands for derivative of our function with respect to z. The second is what we call as for subtraction. Same thing, if you have here f of z, but minus g of z, the derivative of such, the difference of two functions is, of course, the derivative of the first function with respect to z minus the derivative of your second function with respect to z. This time, we can no longer interchange them, unlike in the sum, where, of course, if we're going to start with this, before that, it's just equivalent to the original form. But for subtraction, it's very important that the order of functions matter. The third one, okay, is, of course, for the product. The product of two functions. So if we're going to take the derivative of the product of the two functions with respect to z, we are going to use the same rule for the derivative of a function in real numbers, where we take the first term, then we take the derivative of the second function. So it's not necessarily a term, but function. Okay, so take the first function, multiply with the derivative of the second function, then plus you take the derivative of your first function with respect to z times the second function. Okay, so this is also the same with the rules on differentiating a product of two functions in the real numbers. It's just that this time we're using z instead of x. By the way, I forgot to mention, if in other form, it's also equivalent to this, right? Minus g prime of z. That would mean for the product, we know this to be equivalent to your first function times the derivative of the second function plus your derivative of your first function, okay, times the second function. This is addition, so we can, of course, interchange the two combination of results because it's just the same under commutativity. Let's have the fourth one. To complete the basic four fundamental operations, we have the ratio of the two functions. Okay, and if we're going to take the derivative of it with respect to z, we also need to copy or pattern it with the rule for the quotient in real numbers, where we take the denominator, right? Then the derivative of the first your numerator minus your numerator, okay, times the derivative of your denominator, all over the square of, the square of the denominator itself. Okay, by the way, all of these rules can also be proven, as mentioned, using a definition, but we're not going to show the proof of them. Probably we will have videos later on proving each of these rules. So basically, we have here for the quotient, by the way, this is given that our g of z is not equal to 0, okay? So that it will still be defined. This is equivalent to low, that's the shortcut, right? Low, the high, or low, the denominator, times the derivative of the numerator, high, minus high, the low, okay? That's some of the mnemonic techniques for this, over low squared. Similar thing, okay, just different notation. We are using prime instead of this expression here. So these are the basic 4, okay, rules on differentiation. But of course, we still have more of them. Okay, I'm talking about, probably I'm going to present here the remaining. I'm talking about the derivative of a composite function, which is, of course, we know as chain rule. Okay, chain rule is actually, we know as the derivative of composite function. Let's say f of g, this case z, is equivalent to f of g of z, meaning the z component of your f becomes another function and it's g itself. The chain rule allows us to talk about this one because a lot of functions will have to use this chain rule, and this is also the same with the chain rule for our product. I mean, that's our product. Chain rule for our real numbers. Okay, so the idea here is to get the derivative of that is, of course, we're going to take the derivative, okay, of your function as a whole, okay, treating this as one object or one value. Then you're going to multiply this by the derivative, okay, of your interior function, okay. So g of z, or in other form, we have here f prime of your g of z, treating this as 1, okay. So we're going to look at it as a component of, I mean, as a function of f itself. Then before we end, we're going to multiply it with the derivative of the internal function itself. It's called chain rule because it looks like this, okay. We know that this to be chain rule because we're going to use the outer dimensions or function first, then we take the inner, just like that. If our function here, I mean our z for g is also another function, so we're going to do the same thing all over again. That's why it almost looks like a chain, okay. That's why it's called chain rule, okay. These are some basic rules of differentiation, but let me add one more thing because I forgot to add it here. We have the constant, okay. I'm talking about, say for example, if you have c times f of z, okay, meaning it's a function where it's a multiple of f. C is any constant, okay. Let's call it 5. So for example, our function can be, there is another constant multiplied to that. The derivative of that is, of course, we know this to be, okay, the derivative, I'm going to place here. By the way, I forgot to make some notations here, okay, so that you will not be confused. So I'm going to take the derivative with respect to z, okay. So this is actually, you can move out, sorry for that, you can actually factor c first, then you take the derivative of your function z. So the constant c may be considered to be factored, and later on apply this to this one here. Or of course, in other form, this is c times f prime of z. Okay, these are some basic of the rules. You also have other forms, especially for a special derivative for trigonometric functions, exponential functions, and so on and so forth. So these are just basic rules for differentiation for complex numbers, which are also applicable and true in pattern to the functions in real numbers. Thank you very much for watching.